Okay, example 8.5. We have a box of books right here, all right, and it's being lifted vertically from rest over some distance. So what we're going to be asked to do is to find the work done by the lifter up, the work done by gravity downwards, and the final speed of the box. All right? So let's start writing down things that we know about this. The mass of the box equals, and in fact, I'm going to write in a different color so you can see it a little bit, because I'm going to shrink this down so we have some more space. The mass of the box equals 4.10 kilograms. All right? From rest, that's going to be important a little bit later on, 0 meters per second. A distance, d, or you could call it delta x, of 1.60 meters, directly upwards, of course. By what force? Well, the force, and I'm going to call it by a force up, all right, is going to be 52.7 newtons. And what is it that we want to find? Well, we want to find the work done by the person. I'm going to, instead of just saying work done by P, I'm going to call it work up. Okay, that's what we want to find. So that's going to be our A right there. B, we want to find the work done by gravity. And C, we want to find the final velocity of the box, because it's lifted from rest, right? And so as it's force is applied to it, it's going to have a final velocity because it's not going to be at rest anymore. All right, these two seem like they're pretty familiar. This one, final velocity, that sounds like kinematics. And if you thought that, you'd be right, which means we're going to have to bring in that link between work and forces and kinematics. That is acceleration. Acceleration is going to be our link between the two. All right, before we start, let's go ahead and I'm going to just draw a box right here. So here's our box. Not too bad. And let's draw our forces that are on it. Well, force of gravity, also known as mg, is acting straight downwards. Okay? Well, I'm going to make our force of upwards, our upwards force, blue, F UP right there. That's going to be 52.7 newtons, right? And we want to label one more thing, and that is the distance d, and that equals 1.6 meters. All right, and it's being moved directly upwards like that. Okay, you got it? So I'm going to take all that, and well, first thing I'm going to do is shrink that all down. Okay, so let's just go ahead and do that right there. And I'll put that up in the corner. So if it's too small for you, you can probably still read off your sheet. Let's go ahead and let's solve for part A. All right, we want to, that looks like a D, doesn't it? Part A right there. We want to know the work done upwards by the person. All right, well, what's our definition of work? Well, work equals, or work upwards, equals force. Oh, goodness. Try that again. Work upwards equals force upwards times the distance times the cosine of the angle phi between them, right? Well, what's our upwards force? Well, that's 52.7 newtons, right? What's our distance d? That's 1.6 meters upwards, which happens to be in the same direction as a force. And what's the cosine of the angle between them? Well, the angle between them is 0, right? Cosine of 0 degrees, because they're exactly in the same direction. Here's your force, here's your distance, and so there is no angle between them, or the angle between them is 0. Okay? So let's solve for our work done right here. What's 52.7 times 1.6? I get 84.3. In fact, I'm going to save me some space right here. Oh, I thought I could delete that. I guess I can't. Equals 84.3 what? It's joules, right? Joules. So that's the work done upwards by the person. Okay, 84.3 joules. Great. We have that done. Let's do part B now. All right. What is the work done by gravity? That's what we want to know in part B. Okay, well, let's write down our equation for work again. Work done by gravity equals force of gravity times distance times the cosine of the angle between them, right? What's the force of gravity? That's mg. And then, of course, we have our distance and then our cosine of phi. All right, so mg is going to be, what's our mass of our box? That's 1.4, sorry, that's 4.1. 4.1 kilograms. Our g, of course, is 9.81 meters per second squared, and our distance d is 1.6 meters. However, the angle between them is going to be different from before, right? Because here's a direction that the gravity force vector is acting. Here is the distance of motion, the direction of motion, the direction that the distance is in. So that's a 180-degree difference right there. So, oops, times a cosine of 180 degrees. All right, what is the cosine of 180 degrees? That's -1. So gravity is going to be doing negative work right here because it's acting in the opposite in the direction that the thing is actually moving. So what do we get then? If we take 4.1 times 9.81 times 1.6 times, if you really want to, times -1, we get negative 64.3 joules of work that is done by gravity. Work done by gravity is negative 64.3 joules of work. All right, so gravity is working against us. The person lifting it is winning because they're putting out more work than gravity is doing on the box, which is why the box actually moves upwards. All right, but this last part right here is going to be a little more complex because we need to find the final velocity of the box. So I'm going to go ahead and see if I can shrink this down a little bit, all this other stuff here. Okay, like that. Hopefully that makes a little bit more work, or a little more, less work, a little more space for us here. And let's go ahead and start solving for that final velocity. All right, so let's just remind ourselves what we're solving for. V final is what we want. Okay, now remember that velocity is a kinematics value, and that's tied to acceleration, which is tied to force, which is tied to work. So, if you recall, before, we said that net work, that is earlier in our notes, we said net work equals net force times distance. All right, applied over some distance. All right, well, net force is related to acceleration. Acceleration is related to final velocity, so let's go that route. All right, let's solve for net force so we can solve for acceleration and ultimately solve for final velocity. All right, well, net work is force, equals force, net force times distance. So net force, I'm not able to write very well here. Net force, sorry, is net work over distance. Okay? Well, we know that net force is equal to mass times acceleration, so we can write that. Mass times acceleration equals net work over distance. All right, so that means our acceleration, that's a D, that's not an A. Our acceleration is going to have to be our net work over D times mass. All right, well, that's great, you say, but what the heck is net work? Well, it's the sum of all the works that are acting on an object, right? What are the works that are being done to it? Well, we've got work done by a person up here, 84.3 joules, and we've got work done by gravity, negative 64.3 joules. So we can state, okay, well, the net work is going to be 84.3 joules plus negative 64.3 joules, and that should give you a total of 20.0 joules of net work. Let's go ahead and put a dotted line box around that. All right? So that means we should be able to stick that in here and ultimately solve for our acceleration, which we really want to solve for our final velocity, right? Well, let's go back to acceleration there. What's our relationship between acceleration and final velocity? We know that final velocity squared is from kinematics. In fact, I'm going to write it over here to keep it a little bit different from everything else. I'm going to get rid of that right there. Final velocity squared equals v initial squared plus 2 times a times our distance, right? So that means our acceleration, I keep writing my a's as d's, I don't know why. Acceleration equals final velocity squared minus v initial squared over 2 times our distance. All right, well, let's just put these two sides together. Let's set that equal to that, right? Because they're both in terms of acceleration. So I'm going to draw like a box around this because I keep running out of space. And we can say that final velocity squared minus v initial squared equals, over 2 times our distance equals net work over distance times mass. All right, well, that d is going to go away. And let's see right here, we're going to have to multiply up our 2 and bring it up over to this side here, and then add our v initial squared over to that side. So our final working equation for final velocity, and I'm actually, since I'm running out of space, I'm going to allow you to do this, but you can compare it to my final answer. Final velocity squared is going to be net work, 2 times net work, my apologies, 2 times net work over the mass, all plus initial velocity squared. All right, that, my friends, is our working equation for this problem. Oh, well, yeah, it is. If you want to solve for final velocity, you're going to need to take the square root. And the other part of that is that since initial velocity is 0, that's going to go away. But what is the answer that you get for this? If you do your algebra right, here's the answer that I get. Our final velocity is going to be equal to 3.12 meters per second. I'll double box that because this is our working equation, and that is our final answer right there. So we have linked work and kinematics, well, work and energy with kinematics by going the acceleration route. All right, writing what we know about acceleration with regard to kinematics, writing what we know about acceleration with regards to work and force, and then put them together. All right. Now I'll have to admit that was a little bit of a pain to do that, to link all that. You guys are probably agreeing with me. All right, but in the next example, the next little section of notes, we're going to introduce the work kinetic energy theorem, and this is going to make this a lot easier. We're going to basically say that work and kinetic energy are the same thing, and so solving for final velocity is going to be easier the next time we do it. All right, so thanks for watching. I'll see you on the next one.